All right, so my name is Shane Hutson. I'm an associate professor of physics at Vanderbilt University. Secondary appointment in biological physics, which comes in handy for the sort of courses that I teach for our pre-med students. The course I'm talking about is our introductory physics course that the pre-meds all have to take. It's a service course for the physics department. We have pre-med students and engineers who both take introductory physics, but we've split those sections up. So we have a pre-med heavy class that's supposed to have some focus on medical applications of physics, but it's your conventional physics curriculum, right? Newtonian mechanics, motion, waves, thermodynamics in the first semester, and then electricity and magnetism optics in the second semester of it. So we see them for 2 semesters altogether. Class sizes are 60 to 90 students for the most part. We get them as sophomores and juniors. Well, so I have to give credit there to lots of people who have done physics education research over the last 30 years. So I was fortunate enough, and I don't actually remember how this happened, but before the first time I went in to teach one of these introductory physics classes, because it was my second year at Vanderbilt, that I sat down and started reading some of the literature. And for physics, at least, it's pretty advanced, and there were actually books that had been produced. So it wasn't going to all the way back to the primary literature, right? There were Eric Mazur's books, Randall Knight had some, that you could look through and get ideas on what students brought into the classroom. And it was really apparent that they weren't blank slates, that they were bringing in a lot of ideas that had some rational basis, but weren't right. And that those ideas that they brought in were really resistant to change. That no matter how many times a lecturer stood in front of the classroom and told them that those ideas weren't correct, it just didn't sink in. And so you needed to use one of a variety of active learning techniques in the classroom to bring those misconceptions to the forefront and then be able to address them, right? Sort of motivate students to replace them with something else. It was a little disconcerting how accurate the literature was at first, right? It would warn you, all right, on this topic on basic motion, students are going to have some pretty common misconceptions about what acceleration really means, what the signs of accelerations mean, when it's zero, when it isn't. And you start probing and asking questions in the classroom, and yeah, it's there. These students have the misconceptions that the literature said were going to be there. I found the previous literature to be a really good guide in terms of what to expect when I got in the classroom. Yeah, so I can come up with 2 with acceleration right off the bat, right? Acceleration's the time derivative of velocity, and 1, students come in thinking that if the acceleration's negative, that's got to mean something's slowing down. But as physicists, we really mean acceleration negative. It's just really telling us which direction it points relative to our coordinate system. And the other one that's even perhaps more deeply ingrained is this idea that if you have some sort of continuous motion, for example, a ball being thrown up in the air, that it pauses momentarily at the top before dropping down, that its velocity is 0 at the top, and therefore its acceleration must be 0. And it really takes a long time to battle that one out of their prior armory of knowledge. So you throw a ball up in the air, it leaves your hand, and from the moment it leaves your hand, all the way its parabolic arc comes back down and lands in your hand again, it was really subject only to a gravitational force and some air drag, right? A slight modification of that. So its acceleration was largely constant and pointing downward the entire time. And yet students have a hard time coming to grips with the fact that the acceleration was pointing down, and continued to point down the whole time the ball paused and turned around. They think there's got to be something special about that turning point. And in terms of acceleration, there just isn't. Well, so yeah, if you push a little bit on this and you ask them to explain why they think the acceleration's 0 at the top, one of the things that comes pretty quickly to the fore is they bring in a little bit of calculus. They're like, all right, acceleration is the derivative of velocity. It's dv dt. You can see velocity on the top, time on the bottom. And so if velocity is 0, that's got to mean acceleration 0, because I see these 2 things in the equation there. And so it's bringing in some prior knowledge, but not using it quite correctly, right? It hasn't been cemented as we'd want it to be. So what these misconceptions prevent students from doing is having a deep understanding of the physics. If you give them a problem, sort of a conventional problem that's written out, ball starts at X position, has initial velocity Vx and acceleration such and such, they can do the calculation and tell you where it is at some later time, right? They have no problem manipulating the equations till they'll do that all day long if you let them. But if you ask them a deeper question about, right, what's the force on the ball at a different point in time, they have to be able to make this logical chain, right? All right, the ball was turning around, the acceleration was still downward, it was not zero at that point, and so the force was still downward, it was not zero at that point, right? It gets in the way of a deeper understanding that we want them to do. And if you move anything beyond sort of the one-line calculation where they can pull one equation out, put some numbers in and get an answer to it, where they have to chain 2 or 3 logical steps together, they don't know how to make the jump from one logical step to the next, because they don't have, that's where you need the conceptual understanding of the physics to be able to do it.